So here on this slide, you see a mass spectra of using electron spray, a partial ESI of the BSA, and the molecular weight of the neutrals after charge deconvolution. So you see that here we can find out some clues about what happened inside the mass spectrometer. That is, right, in this BSA, there was a dimerization. And how do we know it? Because we see that if you have B, this is the molecular mass of the monomer, and you see twice the MZ value of this number. So the only indication is there's a dimerization, right? And however, you can also say that when the dimer takes in the place of a 2+ charge, right, then you can also have the same MZ value, right? And in this case, if you go down to the lower MZ value, you see that this belongs to the monomer, because after some groups fragment from the whole entity of the monomer, this is what you get. How to explain these kind of signals here? And the only way is that you have a dimer of your non-covalent BSA, then you do some fragmentations, you can have these values. So I think from here the picture is you can look at whether you have a dimerization of the substrate here, and that's a way to possibly explain some of these signals. And of course, you have this charge deconvolution to have the absolute signal of the whole analyte. Now in the next spectral here, I would like to see the two parts. One is the low resolution of the mass spec, and then high resolutions. Now here, I would like you to focus on this part first, right? So you notice that, right, this signal is about be close to 17,000, but this is the most 16950. Now this signal refers to myoglobin. This myoglobin, when it's very fine, when we zoom out here, we just see a line, right, somewhere here. Then we zoom in closer, then we see this line. But if you zoom in even closer, we have a signal, but this is like a triangle. But if you have a high resolution in which you have 512K thousand data points, right, then in fact the signal belonging to the myoglobin is many fine lines together in a similar fashion like your NMR, the nuclear magnetic resonance, when you have the multiplet. This is how it looks like, but you only get that for high resolution. So when you go back to a low resolution, this means you have the zero charge spectrum. Then you can find exactly what is the molecular mass, the peak signal. Then you just go down, okay, 16949, for instance. This is the whole MR. Now, so this zero charge doesn't mean no charge, right? I would like you to deconflict this idea, because we mentioned that if a fragment has no charge, it's not detectable by the transducer in the mass spectrophotometer. So when you say zero charge here, means that it is it's either positive or negative, but there's no fragmentations, and we're referring to this term undergoing low resolution. Okay, no charge means not 2+, 3+, those kind. Just a very tiny single plus charge for a very complex molecule. Now, let's look at an overlay of 3 different kinds of resolution. You see that when you go for high resolutions, going close to 50 ppm, right? Then you see that the signal become like, multiplets lines forming a curvature. So when you have a low resolution here, you just see a little hill, right? I don't see fine lines. But when you go down, you see many different peaks. The reason is that when you have a molecular mass of 15,300, this means you have many carbon, you have many different isotopes, and carbon itself already has 3 isotopes, carbon 12, carbon 13, 14. So you have a +1, +2, plus many carbons there, and of course it's not even including a sulfur, fluorine, chlorine, and other elements where they have different atomic mass and also isotopes. So therefore you have different signals adjacent to it, and it can range from almost a 15290 all the way to a 15315 here. And you look at the range, it is half of 100, like 50. That range is not surprising. Okay. So in this slide here, you see this nano ESI spectra of anti-HIV drug, with ethanol as a solvent in the presence of some ammonium chloride salt. And on the top is the positive ion ESI MS, and the bottom is a negative ion ESI MS. And you can see that because you have the structure of this drug, this anti-HIV drug, right? You just put it out, and then you can find the molecular formula. you can calculate the MR, which means you can see that, right, this is your molecular ion peak, and you see that this is 324.3, right, with M plus H, plus 1. And here at the bottom, because it's negative, is M minus H, M minus 1, and so it's 322.2. So when you average them, you have the 323. That should be the indication of its normal MR, relative molecular mass. Okay. Here we give a summary diagram here under electrode spray. So I'd like you to look at the axis first, the y-axis and x-axis. We are only considering two parameters. On the y-axis is your polarity. Being super high in polarity are those ionic compounds. And the other end of the spectrum is your non-polar compounds. Now, on the x-axis is your MR. Whether you have your high MR or your low MR here. So as a spread, right, this map here tells you that if you see a compound you want to analyze, you should consider what kinds of electrode spray, right, what kind of ionization you like to have before you inject to your mass spectrometer. So most of it covers if you have a high MR and something that's very ionic, you use electrode spray, ESI for sure. Even if you have low MR, but it's very ionic, just go with ESI because you just make it very ionic. So you can see in general, ionic, right, just go with ESI. Okay, see this way. Now I would like you to focus here. If you have something that is a high MR, but it's on the polar side, you should also go for your electrode spray ESI, but you can also consider other ionization introduced a later part in this series. Now, pay attention to this part here, right? You have your low MR and non-polar region, then we'll advise you to choose a GCMS, your gas chromatography, right? And because it's also very hard to ionize. Now, this part, if you fall within this range here, when you have the sigma of medium, molecular mass, right, and of course polar, but not super polar, super non-polar, then you say maybe you should go for your APCI, for instance. Okay, somewhere in the middle here. Of course, you can consider your APPI if it's somewhere between your non-polar and polar, and it's of a low MR here. Okay. Good. So this part, right, I'd like you to summarize what kinds of ions are formed by ESI here. So first we look at the positive ions. Right, if you analyze non-polar, you have this M plus H, the H plus, or you get M plus your alkaline. Alkaline could be your ammonium, right? So NH4, for instance. We have the analyte being medium to high polarity. You have the same thing, and of course some exchange, right? There's a plus 1 here, and in this parenthesis, you have this cluster of 2M, your dimer plus H, 2M plus alkaline, etc., and they adapt when they join temporarily. But these are your less abundant species. For cation ions and ionic, then you have your C plus, possibly your Na plus, for instance, okay, and this is the N-ion, sodium chloride. On the other side, your N-ion ESI, then you have a non-polar species, N-1. It is pretty much symmetrical, and this A, is N-ion, could be a M plus your chloride, for instance. The same thing here. You have some exchanges and the classes which denotes maybe a dimer interacting to form a dark, but it's of a less abundant species. Here, a final summary of all the consideration of mass spectrometry. I think this is very important. Now, for the inlet, right, how do you inject the sample? Of course, we have MS, in tandem with something else before you separate them before you analyze them. So you have the GCMS, gas chromatography. You have got your direct injection probe, solid probe, desorption probe, flow loop injection, infusion. You have the CMS we talked about in the last series of lecture, your capillary electrophoresis, and your liquid chromatography, LCMS. So you see that these three parts here, these three, we box it with your GC, CE, LC. These are separation methods first, separation signs, and then after it's separated, we analyze them using MS. The rest aren't your separation, it's just like injection. How do we ionize it? Because remember, we need ions to be detectable in MS. So we have got electron impact EI, your CI, right? APCI, APPI, ESI, MALDI, LCMS, and in fact, we talked about it beforehand, so we won't elaborate here. And the consideration could also be the key choice of your compound when analyzed is your solubility, volatility, thermal stability. Because some uses very high energy. And whether the compound is polar. In the previous slide, we talked about the MAT, the MR, the polarity, the solubility in the solvent, right? And molecular mass, high or low, right? And fragmentation, does it even fragment? And how stable are the fragments. So, and the key factors affecting the performance when you choose this kind of inlet ionization mode and even analyzer is, does it have a memory effect? We follow, of course, the key factors in choosing it, but something that we can fine tune in the instrument itself are like the voltage applied, solvent used, what solvent we use, or do we even use additive used? Because with that, we give your mass spectra something a bit more complex. You see the M plus alkaline, right? M plus anion, cation, etc. Now, for the analyzer, we have different kinds of detection mode, and further down to this series, we also explain more towards the mass spectrometry, what different analyzers. But in general, you can have the quadrupole that's mentioned before, right? For low, medium resolutions, ion trap for low, the COF time of flight medium resolution, so this is normal what we do. But for something that's very high resolution that you desire, we use the orbit trap, right? Very high, you can use FT, ICR, also magnetic sector. There's a tandem MS, MS. And what you can change inside this part, the detector, is that the mass range, do we want to detect a certain segment, how resolved it is, the mass resolution, the scan speed. The faster you scan, right, the lower the accuracy, but you can do more scan, right, do more time in the period of time. LD, limit of detections, how narrow, how you want to go down to level. Is it 196.2, 196.23, or 196 for the mass spec value? You've got the mass calibration, resolution, energy setting, etc. Of course, the concentration, the mass of the sample. Many ways you can fine tune this part, so I leave it to you. And I will leave it on the final few slides or just some practice exercises. So you see a mass spectra with ESI of this phage lambda lysozyme, right? And then your A is to calculate the Z, for the peaks at MZ991.5 and the 1274 here. You know what they are, the lysozymes, give you the formula. And for part B is to estimate the molecular mass. And question 3 is, what is a suitable additive to enhance the negative electron spread ionization? Okay, this is found in the slides. I hope you can recover this facts information, just pen it down. And this is not a new diagram for you before, for the nano ESI, right? Why are we choosing cone jet? For whichever reason. So with that, I end the series and I'll see you in class. Cheers.